Hi, Stu Schwartz from MasterMathMentor.com. This is video BC12. The topic is vectors in the plane, and it covers the BC manual, pages 62 through 65. Your pre-calculus course most likely took you through a basic study of vectors. However, there are some aspects to vectors that you may not have seen before, so it is advisable to go through this video to make sure that you understand all the aspects of them, including some new notation. In geometry and physics, concepts such as temperature, mass, length, area, and volume can be quantified with a single real number. This number gives the magnitude or size. So when we say that it is 72 degrees Fahrenheit, that is a measure of temperature, and it is how hot it is. The larger the number, the warmer it is. But force, velocity, acceleration, and momentum involve both magnitude, which is the size, and direction, and cannot be characterized by a single number. These are called vector quantities. For instance, if we are talking about a wind out of the east at 15 miles an hour, the 15 represents the magnitude and the direction is east. That is a vector. To represent these vector quantities, we use a directed line segment as shown in the figure. The directed line segment, PQ, has initial point P and terminal point Q, and we denote its length or magnitude with two lines, PQ, and is written the magnitude of PQ. So vector V is PQ, and its magnitude is written as the magnitude of PQ. Two directed line segments that have the same magnitude and direction are called equivalent. Vectors that have the same direction are parallel. So in the figure, all the vectors to the right of PQ are equivalent. In the graph, we have two vectors, u and v. Vector u starts at the origin and ends at the point 5, 2, while vector v starts at the point -1, 3 and terminates at the point 4, 5. U and v are equivalent because the magnitude of u is equal to the magnitude of v. They are both, by the Pythagorean theorem, equal to the square root of 5 squared plus 2 squared, which is the square root of 29. And each of them makes the same angle with the horizontal. It is the inverse tangent of 2 over 5. So since their magnitude is the same and their direction is the same, the two vectors are equivalent. This can be summarized by the rule shown. If point P is the point P1, P2, and point Q is the point Q1, Q2, then vector V, represented by PQ, is the vector V1, V2, which is the vector Q1 minus P1, Q2 minus P2. The magnitude, which is the length of PQ, which is written as the magnitude of V, is, by the Pythagorean theorem, the square root of Q1 minus P1 quantity squared plus Q2 minus P2 quantity squared. This means that we do not need an initial point and terminal point to represent a vector. So if V represents the vector V1, V2, then V can be represented by the directed line segment in standard position from point P, 0, 0, the origin, to point Q, V1, V2. That means that we can move all vectors to the origin as the initial point. In problem 2, we are given an initial point and terminal point, and we would like to write each as a vector in component form and find its magnitude. We will also graph the vectors. In A, we have our initial point is 3, 8, and our terminal point is 6, 12. So our vector is 6 minus 3, 12 minus 8, which becomes 3, 4. So the magnitude of that vector is the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. We see the initial and terminal point in blue, and then we see the corresponding vector in red. Those vectors are equivalent. In B, we have the initial point 4, negative 6, and the terminal point negative 1, 2. So the vector can be written as negative 1 minus 4, 2 plus 6, which is negative 5, 8. The magnitude of that vector is the square root of negative 5 squared plus 8 squared, which is the square root of 89. So we see the initial point and terminal point in blue, and the corresponding vector, which starts at the origin and is in red. In C, we have our initial point as 1/2, 1/3, and our terminal point is negative 1/2, negative 1/6. So the vector can be written as negative 1/2 minus 1/2, negative 1/6 minus 1/3, which is negative 1, negative 1/2. The magnitude of the vector is the square root of negative 1 squared plus negative 1/2 squared, which is the square root of 5 over 2. In the graph, we see the initial and terminal points in blue and the corresponding vector in red. Again, these two are equivalent. When we use vectors, we must be prepared to work with them both geometrically and algebraically. Let's start with the geometric. We have two vectors, u and v, u in red, v in blue. Let's do some operations with them. First, negative vectors. When we negate a vector, all we do is change its direction. So in the case of u, which was going up to the right, negative u will now go down to the left, but will have exactly the same magnitude. The same is true with v and negative v. Vector addition. Remember that a vector can be picked up and moved anywhere in the plane. So when we want to see the result of u plus v, we keep u where it was originally, but we will now draw v tails to heads with u. The resultant vector u plus v starts at the tail of u and ends at the head of v. So we see the u plus v vector in green. It does not matter whether we do it u plus v or v plus u. We will get the same result. Vector subtraction. Remember that u minus v is the same as u plus negative v. So instead of adding v, we're going to add negative v, which we calculated in the second picture. So again, we draw the vector's head to tail, and u minus v is shown in green. Scalar multiplication. We start with vector w in red. 2w will be the vector which is twice as long as w, but in the same direction. Negative 1/2 w will be the vector that is 1/2 the length of w, but in the opposite direction. For instance, winds are expressed in the direction from which they come. So W might be a southwest wind blowing at 10 miles an hour. Therefore, 2W would be a southwest wind blowing at 20 miles an hour, while Negative 1/2 W would be a northeast wind blowing at 5 miles per hour. We have a series of algebraic rules which will make total sense when we see the examples. We have vector u, which is u1, u2, vector v, which is v1, v2, and scalar k. First, the scalar multiple of k and vector u is the vector ku, which is k times the vector u1, u2, which is ku1, ku2. So we simply multiply k by each component of the vector. The vector sum of u and v is the vector u plus v, which is u1 plus v1, u2 plus v2. We simply add the components. The negative of vector v is negative v, which will negate both components. So it becomes negative v1, negative v2. The vector difference of u and v is the vector u minus v, which is u1 minus v1, u2 minus v2. We simply subtract the components. And finally, the magnitude of vector kv is the magnitude of k vector kv, which is the magnitude of k times the magnitude of v. In number 3, you are given vectors u equals negative 3, 7, and v equals 5, 1. There are 8 expressions you are to calculate the value of. In A, you are given negative 1/2 u. So we multiply both components by negative 1/2 and we get 3/2 negative 7/2. B asks for the magnitude of vector negative 1/2 u, which will be the square root of 3/2 squared plus 7/2 squared, or the square root of 9/4 plus 49/4, or 1/2 square root of 58. C asks for u plus v, so we simply add the components. Negative 3 plus 5, 7 plus 1, and we get 2, 8. D asks for the magnitude of that vector, which is the square root of 2 squared plus 8 squared, or the square root of 68, or 2 square root of 17. E asks for u minus v, so we subtract the components. Negative 3 minus 5, 7 minus 1, or negative 8, 6. F asks for the magnitude of that vector, which is the square root of 64 plus 36, or 10. G asks for 3u minus 4v. So 3u is negative 9, 21, and 4v is 24. So we subtract the components and we get negative 29, 17. And H asks for the magnitude of that vector, which is the square root of negative 29 squared plus 17 squared, or the square root of 1,130. We define a unit vector as a vector in the same direction as the original vector, but with magnitude 1. If v is a non-zero vector, then its unit vector is calculated by v over the magnitude of v. The unit vector for u, negative 3, 7, is u, the vector negative 3, 7, over the square root of 58, which is the vector negative 3 over the square root of 58, 7 over the square root of 58. We now take the magnitude of u over the magnitude of u, which is the square root of 9/58 plus 49/58, and that is 1. The unit vector for v, 5, 1, is v over its magnitude, which is the square root of 26. So we get vector 5 over the square root of 26, 1 over the square root of 26, and the magnitude of that is the square root of 25 over 26 plus 1 over 26, which is 1. Finally, we want the unit vector for u plus v. U plus v was calculated in part C above as the vector 2, 8, and we divide it by its magnitude, which was part D, 2 square root of 17. So we get the vector 1 over the square root of 17, 4 over the square root of 17. When we take the magnitude of that vector, we get the square root of 1/17 plus 16/17, which is 1. While vectors may not be new to you, as you may have studied them in pre-calculus, we want to show another notation that is used that you probably have not seen. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors. We know they're unit vectors because their length is 1. And they are denoted by I, which is the vector 1, 0, and j, which is the vector 0, 1. We see them in the graph. I is in blue, j is in red. This notation can be used to represent any vector. So if we have the vector v containing the components v1, v2, that can be written as v1 times the vector 1, 0 plus v2 times the vector 0, 1, which in turn can be written as v1i plus v2j. We call this v1i plus v2j a linear combination of I and j. The scalars v1 and v2 are called the components of v. So the vector 5, 3 can be written as 5i plus 3j. The vector negative 2, negative 1 can be written as negative 2i minus j. The vector 7, 0 can be written as 7i, and the vector 0, negative square root of 2 can be written as negative j square root of 2. Over the years, many mathematicians have developed vector theory, and many use their own notation. One of the reasons for this unit vector notation is that many keyboards did not have vector notation on them. Some books use the greater and less than signs, which can be confusing. Others use parentheses, which confuse vectors with points. Others use brackets. This unit vector notation is a standard form today and is adopted by many books. 5 reads, let u be the vector with initial point negative 3, 7 and terminal point negative 5, 2. Let v be the vector 3i minus 2j. Write the following as a linear combination of I and j, and we have 3 problems. First, we must write this as a vector. So u is equal to negative 5 minus negative 3, 2 minus 7, which is negative 2, negative 5. So writing it as a linear combination of I and j is negative 2i minus 5j. B asks for the vector w, which is 2u minus 3v. So w is equal to 2 times negative 2i minus 5j minus 3 times 3i minus 2j. The advantage of this is we treat I and j as regular variables, and w is equal to negative 13i minus 4j. C asks for the unit vector for w, and that is defined as w over the magnitude of w, which is negative 13i minus 4j over the square root of negative 13 squared plus negative 4 squared, which is the square root of 185. So writing this as a linear combination, we have negative 13 over the square root of 185i minus 4 over the square root of 185j. Other than notation, there is a better reason that we use the linear combination of I and j to represent vectors. If v is a unit vector such that theta is the angle from the origin to the point, cosine theta, sine theta, lying on the unit circle, then v can be written as the vector cosine theta sine theta, which is I cosine theta plus j sine theta. We see this in the figure. We have a unit circle, meaning that is a circle with radius 1. We choose a point along that circle, and we can call it cosine theta sine theta. And therefore, the vector from the origin to that point can be written as the vector cosine theta sine theta. And writing it in linear combination form, it is I cosine theta plus j sine theta. This does not only work with unit vectors. If v is any other vector such that theta is the angle from the origin to the point, the magnitude of v cosine theta sine theta, then the vector v is the magnitude of v times the vector cosine theta sine theta, which is the magnitude of v I cosine theta plus the magnitude of v j sine theta. In real life, vectors are usually expressed with a magnitude and an angle. This is particularly convenient for this type of notation. A vector with magnitude 6 at an angle of 60 degrees to the horizontal would be expressed as 6i cosine 60 degrees plus 6j sine of 60 degrees, which is 3i plus 3 square root of 3j. A vector with a magnitude of 8 at an angle of 135 degrees to the horizontal would be written as 8i cosine 135 degrees plus 8j sine 135 degrees, which is negative 4 square root of 2i plus 4 square root of 2j. Number 7 reads, 2 tugboats are pulling a disabled cruise ship due east. One pulls with a force of 40 tons at an angle of 12 degrees to the northeast, and another at 50 tons at an angle of 18 degrees to the southeast. What is the resultant force on the ship, and at what angle does it travel? This is what is occurring. The 2 tugboats are pulling on the cruise ship. If they were pulling at the same angle and also the same force, then the cruise ship would travel due east. But that's not occurring. The tugboat that is pulling south is a bit stronger and has a slightly greater angle, which means it is exerting more force than the ship to the northeast. Therefore, we would expect that the cruise ship would travel just a bit south of east. The first thing we do is draw a realistic picture as to what is occurring. We place the cruise ship at the origin, and we draw our 2 vectors. The vector of 40 is at an angle of 12 degrees and will be north, and the vector that is 50 tons will be south at an angle of 18 degrees. Next, we draw a vector diagram. We keep our 40-ton vector in green, but then move our blue vector to the head of the green vector. Our resultant vector will be the vector from the origin to the head of the blue vector. That is the path of the cruise ship, and the angle with the horizontal is the angle it will travel. Our third diagram just draws the resultant vector and the horizontal and vertical. If we can find the horizontal and vertical, we can find the length of the resultant vector and also the angle to the horizontal, which is the information that we need. Next, we add our 2 vectors. 40i cosine 12 degrees plus 40j sine 12 degrees plus 50i cosine negative 18 degrees plus 50j sine negative 18 degrees. Instead of using negative 18 degrees, we could have used 342 degrees. When you do this on your calculator, make sure you are in degree mode, not radians. And that turns out to be 86.679I minus 7.134J. So the resultant vector will have a magnitude by the Pythagorean theorem of the square root of 86.679 squared plus negative 7.134 squared, which is 86.972. The tangent of the angle is negative 7.134 over 86.679, and therefore theta is equal to negative 4.705 degrees. So our final answer is that the ship is being pulled with a force of 86.972 tons and 4.705 degrees to the southeast. If the two tugboats were pulling the ship directly east, they would be pulling with 90 tons. The fact that it's pulling with 86.972 means that it's only losing about 3 tons by pulling on these angles, which is not a great deal. However, 4.7 degrees to the southeast means that there's going to be needed to be a correction at some point along the line. Number 8. A plane traveling 500 miles per hour in the direction of 40 degrees encounters a wind of 80 miles per hour in the direction of 120 degrees. What is the resultant speed and direction of the plane? Here's the situation. The plane is heading along the red line, and if there is no wind, that's where it would travel. However, there is a wind, a strong wind of 80 miles an hour blowing to the southeast, and it's pushing the plane off course. So rather than it travel along the red path, it will be traveling along the green path. Before we start, we must talk about navigational direction. Recall that when we talk about planes or ships, directions are measured from the north in a clockwise direction. So the plane traveling in the direction of 40 degrees is a 40-degree angle to the north, while the wind at 120 degrees is shown on the diagram as an angle of 30 degrees to the x-axis. On the diagram, we see the vectors of the plane in red and the wind in blue. We next make a vector diagram where we move the blue vector to the head of the plane vector, and the resultant vector is the green vector. That is the path that the plane will actually travel. Next, we add our plane vector and our wind vector. Realize, though, that the calculator measures angles from the horizontal. So the plane traveling in the direction of 40 degrees is really, to the calculator, a direction of 50 degrees. So plane vector is 500I cosine 50 plus 500J sine 50 degrees. The wind vector can be represented as negative 30, or if you want to, 330 degrees. So we add 80I cosine negative 30 plus 80J sine negative 30 degrees, and we end up getting 390.676I plus 343.022J. Showing these figures and angle theta on the diagram, we realize that the length of the resultant vector is the square root of 390.676 squared plus 343.022 squared, which is 519.896. And to get theta, we use the fact that tangent theta equals 343.022 divided by 390.676, and we get theta is 41.283 degrees. So we find that the plane actually travels slightly faster, the wind helps it, 519.896 miles per hour. And again, we want the course, and the course is measured from the north, so it's 90 minus 41.283, or the course is 48.716 degrees. We talked about vector addition, vector subtraction, scalar multiplication, but we have never discussed vector multiplication. There are actually two ways that we can multiply vectors, the dot product and the cross product. We will only discuss the dot product. The dot product of two vectors u with components u1, u2, and v with components v1, v2 is given by u dot v, which is u1, v1 plus u2, v2, which is a scalar. So we multiply the two components and add. So the product of two vectors is not a vector, it is a scalar. So in number 9, we are given that u is equal to the vector -2, -2, and v is the vector 3, 9. And we would like to do 5 different calculations. In A, u dot v is -2 times 3 plus -2 times 9, which is -6 minus 18, which is -24. Note that we could have also done v dot u and gotten the same answer. B, -2 u dot v. We can factor out the -2 and write it as -2 times the quantity u dot v. And since we've already calculated u dot v, we get -2 times -24, which is 48. We could have also calculated -2u and dotted that with v. C, u squared is simply u dot u, which is -2 times -2 plus -2 times -2, which is 8. Same with D, v squared. That is 3 times 3 plus 9 times 9, which is 90. E is a bit more challenging. U squared v dot uv squared. U squared is a scalar, so multiplying that by v gives a vector. V squared is a scalar, multiplying that by u, that gives a vector as well. So this is really a vector times a vector, and our answer will be a scalar. U squared is 8, which we previously calculated, times 3, 9. And we will dot that with uv squared, which is 90 times the vector -2, -2. So this becomes 2472 dotted with -180, -180. And now we just have the math, 24 times -180 plus 72 times -180, and our answer is -17,280. It is not clear why the dot product is calculated this way, or what it really even represents. This is covered extensively in multivariable calculus, but here is an application. The geometric interpretation of the dot product is the length of the projection of u onto v. If there were a light shining from a direction perpendicular to v, the dot product is the length of the shadow of u onto v. If the dot product is 0, there is no projection of u onto v. And if the dot product is negative, the projection of u onto v is on the opposite direction of v. Two vectors u and v are called orthogonal if their dot product u dot v is equal to 0. In terms of geometric interpretation, this makes sense. If there is no projection of u onto v, then the two vectors must be at right angles to each other. Orthogonal, perpendicular, and normal all have the same connotation. However, we say that vectors are orthogonal to each other, lines are perpendicular to each other, and a line is normal to the curve. So in the third picture, we see the curve in red, we see the tangent line in green, and the line normal is perpendicular to the tangent line, and we call that normal. When vectors are given in terms of magnitude and direction, it is easy to find the angle between them. But when they are given in component form, finding the angle between the two vectors is much more difficult. There is a neat formula that ties together the vectors and the angle between them. It says that if theta is the angle between u and v, then cosine theta is equal to u dot v over the magnitude of u times the magnitude of v. In number 10, we are given that u is equal to 3, negative 1, v equals 4, 3, and w equals 2/3, negative 8/9. And we would like to find the angle between each vector pair. For A, finding the angle between vector u and v, we say that the cosine theta is equal to the dot product of u and v, which is 12 minus 3, over the magnitude of u times the magnitude of v. The magnitude of u is the square root of 10, and the magnitude of v is 5. When we take the inverse cosine of this expression, we get 55.305 degrees. Again, make sure you are in degree mode. In B, we want to find the angle between vectors u and w. So theta will be equal to the inverse cosine of the dot product of u and w, which is 3 times 2/3, plus negative 1 times negative 8/9, over the magnitude of u, which is the square root of 10, and the magnitude of w, which is the square root of 4/9 plus 64 over 81. Let the calculator do all the work, and you end up with theta is equal to 34.695 degrees. In C, we would like to find the angle between vector v and vector w. So theta is equal to the inverse cosine of the dot product of v and w, which is 8/3 minus 24/9, which is 0. Since the two vectors are not the same, then theta is equal to the inverse cosine of 0, and it turns out that we get 90 degrees, which means that these two vectors are orthogonal to each other. Notice we've gone through an entire video without even once mentioning the words derivative and integral. In the next video, we will be looking at vector-valued functions, which will allow us to use limits, derivative techniques, and integrals on vectors, allowing us to do a lot of neat types of problems. Stay tuned.